This presentation illustrates the main processes of the reference model developed by the European Framework Platform 7 project, Common Operations of Environmental Research Infrastructures, or ENVRI for short. The ENVRI reference model is an abstract conceptual model intended to describe the data and computational requirements of environmental research infrastructures. The main processes occurring in such systems are described by comparing viewpoints. The presentation is part of a threefold training program and has been produced by the development team of the ENVRI reference model. The intention of the ENVRI reference model is to help a community reach a common vision, to provide a common vocabulary for communicating concepts, to provide a uniform framework into which components of different research infrastructures can be placed and compared, to provide standard solutions to common problems, to secure interoperability between different implementations of services, to enable reuse and sharing of resources and experience, as well as to avoid duplication of effort. A uniform framework makes it far easier to design research infrastructures in the construction phase, as it helps to define roles, processes, and tasks in operations, to identify missing or duplicated actions, to define requirements of IT components, to enable a modular approach for the research infrastructure IT solutions, making possible to use external suppliers for the component development, and it supports cross-disciplinary perspectives and products. Thus, the benefits of a reference model range from immediate, because it helps in the construction phase, to long-term, as it provides standard solutions enabling data usage and communication between the research infrastructure's commonplace. The ENVRI reference model is based on the Open Distributed Processing (ODP) framework for distributed systems, which defines 5 specific viewpoints. The enterprise viewpoint concerns the organizational situation in which business takes place. The information viewpoint deals with the modeling of the shared information manipulated within the system of interest. The computational viewpoint concerns the design of the core services, applications, and interfaces between components provided by the system. The engineering viewpoint tackles the problem of how to distribute functionality across a distributed infrastructure. The technology viewpoint concerns real-world constraints applied to existing computing platforms on which the computational processes must be executed. The first version of the ENVRI reference model concentrates on 3 of the 5 viewpoints. First, the enterprise viewpoint, which focuses on the organizational situation of research infrastructures. In order to better fit with the sensibilities of the ENVRI community, it will be referred to as the science viewpoint from here on out. Also, the information viewpoint and the computational viewpoint, focusing on critical data and computation requirements needed by all environmental research infrastructures. In a future implementation, it is foreseen to include also the engineering and the technology viewpoints, but in this presentation, they will not be addressed in any further detail. This presentation concentrates on the correspondences between the different views of selected processes. The science viewpoint defines community with its community behaviors and its members' roles within an infrastructure. Agents within a community collaborate to achieve certain objectives. A behavior is a composition of actions performed by roles assumed by members of a community. A role can be either active, typically associated with a human actor, or passive, typically associated with a non-human actor. The information viewpoint defines information actions and information objects. Information actions model the information processing in the system. Every action is associated with at least one object. An action creates an object, or it causes state changes in the objects that participate in it. An action can precede another action, or it can delegate to a further action. Information objects are used to model various information entities manipulated by the system. An information object can be part of another information object and can take part in an information action. The computational viewpoint defines computational objects. These encapsulate a set of functions and provide a number of interfaces by which that functionality can be invoked, or by which the object can invoke the functions of other objects. Operational interfaces are used to pass messages between objects used to coordinate general infrastructure operations, such as querying a data resource or configuring a service. A given operational interface must be either a client interface providing functions by which operations can be invoked on other objects, or a server interface providing functions to be invoked by other objects. The corresponding interfaces must fit to each other. Stream interfaces are used to deliver large volumes of data from one part of the infrastructure to another. A producer interface streams data to one or more bound consumer interfaces, as long as there is data to transfer and the consumer is available to receive that data. Some computational objects are able to create or instantiate other computational objects in response to some dynamic functional requirement. On the right side of the slide, you can see the notation used in diagrams, and also in this presentation, where operational interfaces are linked using ball and socket notation. Clients expose sockets, half circles, while servers expose balls, closed circles. Stream interfaces are linked using a double arrow notation. The arrowhead points away from the producer towards the consumer. The ability to create objects is noted by a single filled arrow extending from the creator object to the object being created, with the annotation New Object. In the following slides, you will see a number of processes illustrated, each described from the three different viewpoints of the ENVI reference model. You will detect three different types of correspondence. Between the science and information viewpoints, each community behavior corresponds to an information action. Between the information and computational viewpoints, each information action may correspond to a computational interface. Between the science and computational viewpoints, each community behavior may also correspond to a computational interface. In the ENVI reference model, a number of processes are designed for the data acquisition subsystem, the data curation subsystem, the data access subsystem, the data processing subsystem, and the community support subsystem. In this presentation, only a selection of processes will be explained in detail. Instrument configuration, raw data collection, data curation, data annotation, and finally data query. Instrument configuration is modeled in the science viewpoint as a behavior of the data acquisition community, performed by a technician that sets up a sensor or a sensor network. In the information viewpoint, instrument configuration is part of the action that specifies the details of the measurement, like measurement device types and measurement details. As a result of this action, the information object specification of measurement is created. In the computational viewpoint, an acquisition service object encapsulates the computational functions required to monitor and manage a network of instruments. An acquisition service can translate acquisition requests into sets of individual instrument configuration operations as appropriate. An acquisition service should provide the client interface configure controller, which is used to configure data collection on individual instruments. An instrument is considered computationally to be a source of raw environmental data managed by an acquisition service. An instrument controller object encapsulates the computational functions required to calibrate and acquire data from an instrument and thus provides the configure controller server interface, which configures how and when an instrument delivers data to a data store. The instrument configuration behavior corresponds to the specify measurement action, which corresponds to the configure instrument operational interface in the computational viewpoint. Thus, the instrument configuration behavior in the science viewpoint also corresponds directly to the configure instrument interface. Raw data collection is a behavior of the data acquisition community, performed by a data collector that controls and monitors the collection of digital values from a sensor instrument, or a human sensor, such as a measurer or an observer, associating with the data consistent timestamps and any necessary metadata. In the information viewpoint, the specification of the measurement or observation is used in the actual act of measurement or observation, which creates a measurement result. In the computational viewpoint, the instrument controller acquires data from an instrument and provides the request data server with functions to directly request data from an instrument. It has a deliver raw data producer interface to deliver raw data streams to a designated data store. The raw data collector is a data transporter encapsulating the functions required to move and package raw data collected by the data acquisition subsystem. It provides a request data client interface to retrieve data from a given data source, and it has a deliver raw data consumer interface to collect raw data sent by instruments in the data acquisition subsystem. There is a correspondence between the data collection behavior and the perform measurement observation action, as well as between the perform measurement observation action and the request data operational interface and the deliver raw data stream interface. As such, exists there also a correspondence between the science and the computational viewpoints. Data curation is represented in the science viewpoint by behaviors of the data curation community, such as data preservation, which is performed by a data curator that deposits data, metadata, and other supplementary information according to established data preservation policies, and data replication, which is performed by a storage administrator that creates, deletes, and maintains the consistency of copies of a dataset on multiple storage devices. In the information viewpoint, the measurement results object takes part in the store data action that results in new persistent data. This raw data takes part in the backup data action to ensure that backups of the data are created. In the computational viewpoint, the raw data collector is considered responsible for packaging any raw data obtained into a format suitable for curation. This may entail chunking data streams, assigning persistent identifiers, and associating metadata to the resulting datasets. It provides the Update Records client, which is used to directly annotate existing datasets curated within one or more data stores, and an Import Data for Curation producer interface, which is used to deliver repackaged raw data to data stores in the data curation subsystem. Data stores record data collected by the infrastructure, providing the infrastructure's primary resources to its community. A data store controller encapsulates the functions required to store and maintain datasets and other data artifacts produced within the infrastructure within a data store, as well as to provide access to authorized agents. A data store controller provides the Update Records server with functions for editing data records within a data store, and an Import Data for Curation consumer interface, which receives data packaged for curation within the associated data store. There are two correspondences between the science and information viewpoints. The data preservation behavior corresponds to the store data action, whereas the data replication behavior corresponds to the backup data action. The store data action corresponds to the update records operational interface and the imports data for curation stream interface. Again, there is a correspondence between the data preservation behavior and the interfaces just mentioned. In the science viewpoint, the data annotation process is part of the data preservation behavior performed by the data curator who deposits annotations into data storage in order to be able to assign directly descriptions to data resources. In the information viewpoint, a local concept, which is part of a local conceptual model, takes part in the annotate data action, which modifies the state of some persistent dataset. A conceptual model is a structured or unstructured collection of concepts, such as a glossary, thesaurus, or ontology, with their attributes and relations. The description of a concept defines the concept in a human and machine readable form. Conceptual models can be fused with the data or kept separately. A local conceptual model is a model developed within a project which should in the harmonization procedure be mapped to a global, widely accepted conceptual model. In the computational viewpoint, the annotation service collects the functions required to annotate datasets and collect observations that can be associated with the various types of data managed within a research infrastructure. It provides an annotate data service interface with functions for requesting the annotation of existing datasets or the creation of additional records, such as qualitative observations made by researchers. It also provides an update records client interface, which is used to directly annotate existing datasets curated within one or more data stores. The data broker is a broker for facilitating data access and upload requests. A data broker object intercedes between the data access subsystem and the data curation subsystem, collecting the computational functions required to negotiate data transfer and query requests directed at data curation services on behalf of some user. The data broker provides an annotate data client interface which is used to request annotation of data held within the data curation subsystem of a research infrastructure. The data store controller provides an update records server interface with functions for editing data records within a data store. There is a correspondence between the data preservation behavior and the annotate data action, and between this action and the annotate data and update records operational interfaces. As such, there is also a correspondence between the science and the computational viewpoints. Data query is part of the data discovery and access behavior of the data publication community performed by the data consumer. In the information viewpoint, the published metadata takes part in the query metadata action. This precedes the query data action. This two-step approach occurs when using OGC services. First, a web feature service is invoked to obtain feature descriptions. Then a web map service is invoked to obtain map images. But a one-step approach is also possible when data is directly annotated and queried using SQL services or SPARQL endpoints. Querying curated data resources requires that the request is brokered by the data access subsystem before any results will be retrieved from the data curation subsystem and delivered to the client from which the source came. In the brokered data query model of the computational viewpoint, any kind of virtual laboratory that enables interaction between the data user and the functions provided by the research infrastructure is able to query the data held within a research infrastructure, subject to access privileges governed by the security service. Data requests are forwarded to a data broker within the data access subsystem, which will interpret the request and contact any internal services needed to fulfill it. In this case, the data broker will invoke the catalog service via its query data interface. The catalog service will locate the datasets needed to answer any given query, as well as any associated metadata, and then proceed to query resources within infrastructure data stores via the data store controller. As you can see, here is used the diagram notation as shown before for space-saving reasons. There is a correspondence between the data discovery and access behavior and the query metadata and query data actions. The data query action corresponds to the query data operational interface. Thus, the discovery and access behavior corresponds to the query data interface of the computational viewpoint. Thank you for listening. This was the second presentation within a threefold training program. The first presentation was concerned with introducing the ENVI reference model and providing an overview of the differing viewpoints described by the model, as well as of the basic components used to define the different viewpoints. This presentation explained some of the main processes that must be managed by an environmental research infrastructure, exploring them from the perspective of the science, information, and computational viewpoints. The final presentation will provide examples of realizations of certain parts of the reference model for different kinds of common components. For further information, please visit the ENVI reference model at the URL shown.